Okay, one of the ways that we can measure the enthalpy change of a reaction is by looking at the reaction itself. And a popular reaction to use when we talk about heat transferring is combustion reactions. So you might see delta HC for heat of combustion, you might just see delta H RXN for heat of reaction, or it might just be delta H. You can figure it out in various ways. One way is by using an energy diagram like this, where we want to know what is the heat of reaction when we go reactants to products, and then we know what the heat of combustion is for the reactants and what the heat of combustion is for the products. So to figure out the heat of formation between these two reactants to products, we can just follow this alternative pathway. Now, it would be additive, so delta or HC2, the heat that was required here, plus the amount of heat that's required over here. However, look at this arrow, it's going the opposite direction. We want to go reactants to products following that pathway. So we would have to flip this arrow, which means we would have to change the sign on that value. So whatever that value is, we would flip the sign. And so we could solve for our heat of reaction, reactants to products, by taking those values if we knew those values. It's a very popular IA topic, looking at different fuel types and seeing how much heat is evolved. Here we're looking at ethanol. You should remember that eth means two carbons. Each carbon needs 4 bonds, and then the OL part means we have a hydroxyl group on it. So we want to calculate the heat of combustion for ethanol. In the lab, what happens is you have a burner, all right, and it's filled of ethanol, and it's going to catch on fire and produce a flame. And then you're going to put a beaker of water over top of it, and you're going to try, your assumption is that your heat is going to heat up that water, so we can measure the temperature change of our water. We know that the amount of heat lost by the ethanol then would be gained by the water, so those two values should be equal, and that's kind of how we can figure this out. Because we know the mass of water, we know the temperature change of water, and we know the specific heat of water. So if we look at section 2 of our data table, it tells you the specific heat of water is 4.18 joules per gram Celsius, or Kelvin. Now we're not using the kilojoules per kilogram because we're given grams. And we can find the heat absorbed by the water. So Q would equal 200 times our specific heat. Now, I know that that gives it to you in Kelvin, but our temperature is in Celsius. However, remember, we're doing the change in temperature. And so if we were to convert the initial temperature and the final temperature to Kelvin, it's actually the same change of temperature. So the fact that one of them is in Celsius and the other one is in Kelvin really doesn't matter. These would both cancel out. And so our grams also cancel, and that tells us we released 10,870 joules of heat. Now that's a very large number, so a lot of times we decrease the size of that by putting it into kilojoules. So we would move the decimal 3 places to the left, 10.87 kilojoules. Now if we look at a balanced reaction, that's for moles of ethanol. We didn't burn a mole of ethanol, we burned 0.45 grams of ethanol. So to be able to equate this to the value in the data booklet, we need to figure out what this is per mole. So we're going to convert grams to moles. So we are going to pull the molar mass of ethanol to the bottom, and we'll put 1 mole on the top. And so we burned 0.01 moles of ethanol. So again, to equate this to what the heat of combustion of methanol is, or ethanol is, we would need to divide So we take our kilojoules and we do it per mole that was actually combusted, and we get 1,087 kilojoules per mole. Now, if we were to look in the data booklet at section 13, we can see that the heat of combustion for ethanol, and it's on the bottom of the first column there, is actually 1,367 kilojoules per mole. Now remember, the negative that's in front of it just means it's being released. So what's the difference? Why are we missing like 300 kilojoules of heat? Where did that go? Well, when you're in lab, one of three things could happen. Maybe not all of the heat transferred into the water, and so you lost some heat to the surroundings. It's going to lose heat to the surroundings unless it's in a completely isolated, insulated container, which is called a bomb calorimeter. And so heat loss to the surroundings is a very well-known, well-established reason. Another reason is that maybe the ethanol didn't completely combust. Instead of the ethanol being the limiting reactant, maybe oxygen was a limiting reactant. So even though we think we burned 0.01 moles of ethanol, we really didn't burn all of that. And then finally, maybe it wasn't done under standard conditions. So remember those standard conditions we talked about in class. That's how we got the value in the data booklet. And so if you're in the actual lab, maybe you're not at the right pressure. Maybe there's something going on. Maybe you're higher up in altitude, and so the pressure is different. So how do we overcome some of these issues? We can graph it. So if we take the initial temperature of the water, so this would be T initial down here, as soon as we start reacting, so as soon as we light the burner and we're burning that ethanol, the temperature of the water is going to increase. And then eventually it's going to kind of level off and even maybe start to decrease because the water starts losing the heat to the surroundings. So if we take a line of best fit, taking this curve, once it's hit that top peak, do a line of best fit and kind of work backwards, we can see where the temperature should have been if no heat was lost to the surroundings. So we're going to move that line backwards. And so our final temperature ends up being up here. So it's not the highest point on the graph, but kind of bringing a best fit line backwards there. And so that's one way of overcoming that heat loss to the surroundings part of doing things in the lab.